morning everyone. So we have our next lecture, lecture number 4, which is based on inverse Laplace transform and system function and system properties. So this is also the topic on basic signals and system, and the code is BEE 303. So this is intended for EN second year students, and EC second year students also can read from this lectures. So in the last lecture we have discussed about Laplace transform, ROCs, region of convergence, and the Laplace transform properties. So in this lecture we are going to see how the ROCs play an important role in calculating the inverse Laplace transform from the Laplace transform itself given in the question. Also we discuss about transfer function, which is system function, and system properties. So there are some system properties like causality or stability, which we discuss here in the case of the Laplace transform. So next we see the properties of the Laplace transform. We already discussed in the last lecture, that is linearity, time domain shifting, Laplace domain shifting, then time and Laplace domain scaling, then conjugation, then time domain convolution, then time domain differentiation, Laplace domain differentiation, and time domain integration. So we have aware of these properties in a simplest way, and you can go through various books which I have mentioned in the last lecture in the references to see the detailed of these properties. So in this lecture we are going to solve some numerical problems based on inverse Laplace transform and also Laplace transform. So the example number 1 is find the Laplace transform of xt, which is ut minus 1. Obviously this ut minus 1 is a shifted version of the ut. So if we draw ut, so this is xt and this is t, and ut is this is xt is equivalent to ut. So ut is basically 1 for t greater than 0 and 0 for t less than 0 in the continuous domain. So when we draw ut minus a, so it starts from a, and this is ut minus a, and this is t, and the value amplitude is always 1. So here we have ut minus 1. So we use here properties, not solving with the basic formula. We generally use here, we are solving with the help of properties which we have mentioned in the last lecture, in this lecture itself also. So if we want to calculate the Laplace transform of xt is equivalent to ut minus 1, what do you think? So firstly we have to take the Laplace transform of ut, which we have already known, that is 1 upon s. Also we know the property, that is time shifting property, that is xt minus t naught, and the Laplace transform of this is e to the power minus st naught x of s. So while using this time shifting property, we can find out easily the value of the Laplace transform of ut minus 1. So here xt is equivalent to ut minus 1, and we know ut Laplace transform of ut is 1 by s, and for this ROC is real of s greater than 0. So here xs is equivalent to e to the power minus s t naught, and in the case of t naught we have the value 1. So e to the power minus s 1 upon s, and the ROC is again real of s greater than 0. So xs is equivalent to e to the power minus s upon s is the Laplace transform of ut minus 1. Using only the properties of the Laplace transform and the transform pair, we have to find out the Laplace transform of this particular question, that is e to the power minus mod t, and the Laplace transform of this is 2 upon 1 minus s square, and the ROC is real of s greater than minus 1 because it has two poles. One is at s equivalent to minus 1 and s equivalent to plus 1. So real of s greater than minus 1 and less than 1. Find the Laplace transform of e to the power 5t e to the power minus mod t. So as we know, the value of Laplace transform of e to the power minus mod t, which is 2 upon 1 minus s square, and this case ROC is real of s greater than minus 1 and less than 1. Using the Laplace domain shifting property, because in the question you can see that there is a multiplication of e to the power 5t, exponential multiplication in the time domain signal will give you the shifting in the frequency domain. So we use here property, this one, e to the power s naught t xt, and the Laplace transform of this is x of s minus s naught. So here what we do, xs is equivalent to 2 upon 1 minus s naught. So in the case of s, in the place of s we write here s minus 5 ka square. for real of s greater than -1 plus 5, because there is a real part consisting of 1 plus 5 and 1 is minus 5. So we have here -1 plus 5 and 1 plus 5. So the real of s belongs to now 4 plus 4 and less than 6. So you have this type of excess. Rewriting x in factored form, you can write it 2 upon 1 minus s minus 5 ka square, and you can write or solve like this, and you will get -2 upon s minus 6, s minus 4. So from here also you have two poles, that is one at s equivalent to 4 and another one is at s is equivalent to 6. Using only the properties of the Laplace transform pair, this we have to find out the similar question, but in a different way. Xt is equivalent to e to the power minus 3 minus mod 3t. So as we know, e to the power minus mod t, the Laplace transform of this is 2 upon 1 minus s square. E to the power minus mod 3t, the Laplace transform of this is 1 upon mod 3, because it is x of 80 in the form of x of 80, 1 upon mod 3, 2 upon 1 minus s by 3 ka square. So by this way you can have the value of real of s greater than -3 and less than 3. When you solve this, that is 2 upon 3, 1 minus e to the power 1 minus s square by 9, and when you solve this you will get the expression which consists of two poles, s equivalent to -3 and s equivalent to 3. So the answer is -6 upon s plus 3, s minus 3. Using only the properties of the Laplace transform, you have to find out there is a convolution property given, that is xt is equivalent to x1 t convolution x2 t, and where x1 t is equivalent to sin 3t ut and x2 t is equivalent to t ut. So we have to find out the value using convolution theorem, and as we know, convolution theorem is x1 t Laplace transform of x1 t convolution x2 t, and this comes out to be x1s x2s. So firstly we have to find out individually x1s and x2s, then we multiply here, and then we take the inverse Laplace transform to find out the value of yt, which is x1t convolution x2t, or xt, which is x1t convolution x2t. How to solve this? So firstly we take x1t, which is sin 3t ut, and for sin 3t ut, the value of x1s is omega upon s square plus omega square, because sin omega naught t, the Laplace transform of this is omega naught upon s square plus omega naught square. Similarly, Laplace transform of cos omega naught t ut also is there, is s upon s square plus omega naught square. So by using this one, sin omega naught t ut, the Laplace transform omega naught upon s square plus omega naught square, we have here omega naught is equivalent to 3. So it is 3 upon s square plus 9. Similarly, t ut, the Laplace transform of t ut, as we know, ut, Laplace transform of ut is 1 upon s, and for t ut it will be d by dt of d by ds of 1 upon s again. So it will be 1 upon s square. So we have both the terms x1s and x2s, then we multiply to get xs. So xs we have 3 upon s square plus 9, 1 upon s square, and when you see, that is 3 upon s square plus 9 for real of s greater than 0, because this term consists of two poles, s plus 3 or s minus 3. It has some complex values. So the answer is s square 3 upon s square plus n. You can also find out by taking inverse Laplace transform the value of xt from this expression. Using only the properties of the Laplace transform pair, we have to find out the Laplace transform of xt is equivalent to t e to the power minus 2t ut, given e to the power minus 2t ut ka Laplace transform, that is 1 upon s plus 2. So here what we do, we take the time Laplace domain differentiation property, and that property is d by dt of xt is equivalent to s xs. One property is this Laplace transform of this, another property is Laplace transform of t xt that is minus of d by ds of xs. There are two properties. This is time domain differentiation and this is frequency domain differentiation. So here we are using frequency domain differentiation. So xs is equivalent to minus d by ds of the given term, that is e to the power minus 2t ut 1 upon s plus 2, and that will be minus d upon ds s plus 2 to the power minus 1, and when you solve it, it will give you 1 upon s plus 2 ka square. So we have the ROC region, that is real of s greater than minus 2, because both the poles are they are existing at minus 2 value. Again, next question, find the Laplace transform x of the function xt is equivalent to t e to the power minus 3 mod t. So, t e to the power minus 3 mod t, we have to rewrite the expression because there is mod in the expression. So, one is multiplied with ut and the another one is multiplied with u of minus t. When t greater than 0, it will be multiplied with ut, and when t less than 0, it will be multiplied with u of minus t. So, rewrite the expression in the form xt is equivalent to, when you t less than 0, then it becomes plus. So, t e to the power 3t u of minus t plus t e to the power minus 3t ut. Now, it's simple to calculate the value Laplace transform of both the expression. Firstly, we calculate the expression for e to the power 3t u of minus t, that is minus of 1 upon s minus 3, for Laplace transform of e to the power minus 3t, 3 of t of u of minus t. And similarly, Laplace transform of e to the power minus 3t ut, and for this we have 1 upon s plus 3. Then using the properties, that is differentiation in frequency of the Laplace transform, you will get the value this. Also, you can calculate with this formula, that is minus 1 upon 1 factorial s minus 3 ka square. Similarly, plus 1 factorial s plus 3 ka square, you will get this value. Now we have a very important theorem, which is initial and final value theorem. So in the initial value theorem, we have to find the initial value of the signal xt, that is at t equivalent to 0. So we write the expression x of at t equivalent to 0 or t equivalent to 0 plus, that is limit s tends to infinity s of xs. So in this type of question, you have been mentioned xs. The value of xs is given. Suppose this is s upon s plus 2, s plus 3, and you have to find out the initial value of this particular thing. So we have x of 0 or limit t tends to 0 plus, like this, x of t is equivalent to limit s tends to infinity x of s, x of s. So limit s tends to infinity s multiplied by s upon s plus 2, s plus 3. So this is limit s tends to infinity s square upon s square 1 plus 2 by s plus 1 plus 3 by 3 upon s, 1 plus 3 by s, like this. So when you put the value of s tends to infinity, it will give you 1 plus 0 and again 1 plus 0, which is the value 1. So by this way, we can calculate the initial value of this particular function, that is xs is equivalent to s upon s plus 2, s plus 3. Similarly, final value theorem gives the final values of the signal xt. So it gives the value at t tends to infinite, and the in the right side we have s tends to 0 as s of xs. So for the final value, limit s tends to 0, when you put limit s tends to 0, s of xs, then it becomes s square upon s plus 2, s plus 3, and then the function becomes 0. So the final value of this particular function is 0 and the initial value is 1. So determination of the inverse Laplace transform. For the inverse Laplace transform, we usually use this formula, xt is equivalent to 1 upon 2 pi j sigma minus j infinity to sigma plus j infinity xs e to the power st ds. But in questions, we use partial fraction method. So find the inverse Laplace transform x of the function xt is equivalent to t e to the power minus 3 mod t. In the same way, then last question we have rewrite the expression. So in the same way we rewrite here expression t e to the power minus t e to the power 3t u of minus t plus t e to the power minus 3t ut. Again taking the Laplace transform, we have the form that is minus 12s upon s plus 3 ka square or s minus 3 ka square. So now we have system functions and system properties. So we have two types of system properties, like first one is the causality. LTI system is causal if its impulse response is causal. A causal function, however, is inherently right-sided. Consequently, from the properties of the ROC of the Laplace transform, the ROC associated with the system function of a causal LTI system is the right half plane or the entire complex plane. For a LTI system with rational function H, causality of this system is equivalent to the ROC of H being the right half plane to the right of the rightmost pole, or if H has no poles, the entire complex plane is the ROC region. So, for the causality, it's necessary the poles or the ROC exist in the right half plane. For the LTI system with each system function, determine whether the system is causal or not. So, first one, real of s greater than minus 1. So, if you draw this real of s and imaginary of s, and this is minus 1. So, real of s greater than minus 1, this is a causal system. The second one is real of s greater than minus 1 and less than 1. So, this is minus 1 and this is 1. And this is the region. So, in this case, the ROC, the function is not causal or it is non-causal. This is causal. Third one is real of s less than minus 1. This is particularly anti-causal. This is causal. This is non-causal. Because anti-causal is why? Because it's the ROC lies on the left side of the plane, real of s less than minus 1. And the last one is real of s again greater than minus 1 is the causal. So, by this way we categorize the causal systems. Next is the stability. A system, LTI system is BIBO stable if and only if the ROC of its system H function contains the imaginary axis or the j omega axis. If the ROC doesn't contains j omega axis, then the system is not stable. A causal LTI system with rational functions H is BIBO stable if and only if all the pole of the H lie in the left half of the plane. Only in that case it will include the j omega axis. Obviously, that is all the poles have negative real parts. So, we check for the stability also in the case of the previous question. In the first case, this is stable because it includes the j omega axis. Second case, it is non-causal but it is stable. The third case, it is anti-causal and unstable. And the fourth case, it is causal and stable because it includes the j omega axis. So, LTI system has the system function 1 upon s plus 1, s plus 2. We have different ROCs, real of s less than minus 2, first one, real of s less than greater than minus 1, real of s greater than minus 2 and less than minus 1. So, we have to check whether it is stable or not. So, the first case, real of s greater than minus 2, which is not a possible ROC, because real of s less than minus 2 is a possible ROC, but it is anti-causal and also unstable. So, this part is anti-causal and unstable because it does not include the j omega axis and also not on the right half plane. Real of s greater than minus 2 and less than 1. So, in this case, the second case is the non-causal and unstable. And the third case, real of s greater than minus 1, this is causal and stable because it includes the j omega axis also. So, LTI system and differential equations, we have different differential equations. By that differential equation, we can find out the value of the transfer function or system function, which is Hs is equivalent to Ys upon Xs. So, consider this expression y d2 yt upon dt2 plus dyt upon dt minus 2 yt. We have to find out the system is causal, system function, impulse response st, and also the system is causal, stable, or the system is neither causal nor stable. So, we solve this taking Laplace transform s square ys plus sys minus 2ys is equivalent to xs, and then we find out the value of the hs, which comes out to be this, and this is your system function. Next, we find out using the partial fraction method, we find out the value of ht. Also, we can have ht, and then we see whether it is stable or not. If it is absolutely integrable, then it is stable, and if it is not absolutely integrable, then it is not stable. So, in the first case, real of s greater than 1, it is causal but not stable. Real of s lies between minus 2 and 1, it is non-causal and unstable. And real of s next is less than minus 2, it is anti-causal and unstable. So, the only first case, which is real of s greater than 1, is causal. All the cases, and the second case is stable. So, this is causal and unstable. This is non-causal and stable, and this is anti-causal and unstable. So, these are the references of this particular lecture. You can read these books to get a glimpse of this particular lecture and solve numerical problems. And in next lecture, we will see the Laplace transform or some other topic, which is a complex topic, lecture number 5. So, we will meet soon in the next lecture.